Hello, welcome to Latency Exchange. On this channel we discuss technical topics relating to low latency trading, concentrating on the exchange side concepts, technologies and processes. I'm Dave Beattie, a solutions architect specializing in low latency exchanges. In this first series of videos I will detail my architectural solution for a 24/7 low latency exchange. In this video we will look at the function and tuning of the matching engine and how it supports the requirements of the non-stop low latency exchange. In order to support the exchange, the matching engine server has a number of discrete functions. Firstly, the communications module receives, verifies, and deduplicates messages from the separate physical network cards. Once this is done, it passes the messages on to the queuing function. It can do this directly into a message queue or preferably via a message bus. The message bus is internal to the matching engine server. Separate topics can be used on this bus for separate asset classes or matching engine instances. This ensures that the enqueuer gets a steady stream of non-conflicting messages. The enqueuer takes relevant messages off the bus and adds them to the bid or offer queues of the respective matching engine instance. These are sorted by price and then by timestamp. It's a matter of business policy to determine if the timestamp to be used should be the matching engine timestamp or the initial gateway timestamp. Depending upon the relevant application logic, the matching engine scans these queues for viable trades, either on a continual basis or triggered by the arrival of a new message. When a viable trade occurs, the matching engine follows its normal logic and places the matched trades back on the message bus. Finally, the communications module takes this message and sends it out of the relevant physical interfaces. The message bus can be monitored by other processes for logging and synchronization with peer matching engines. A dedicated matching engine instance is used for complex trades, such as swaps. This engine separates complex trades into their constituent parts, while controlling each part so that the trade will only happen if all parts complete. It's also responsible for control of time-based trades, such as good till date. On top of this architecture, we add the command and control module. This is able to take information from the reference data server to configure its matching engine instances. This data contains not only the rules of operation for the exchange as a whole, but it also contains the trading parameters for all the individual trading institutions. This module is also responsible for instructing the matching engine when to stop or start processing messages, that is to say, when it needs to change roles. The principal aim of the matching engine is to match bids and offers as quickly as possible. This is a key factor in the overall performance of the exchange. As such, it should only be undertaking the tasks that it absolutely has to. Furthermore, it should be trying to complete those tasks as quickly and efficiently as possible. Normal best practice tuning should be applied to these servers. All transaction data should be accessed from memory, not from disk. There should also be sufficient memory to negate the necessity for a swap file. This means that this system does not have to be particularly fast. Generally, the communications module, the message bus, and the matching engine instances should be pinned to high priority CPU cores. Other processes do not need to be pinned. This means that these high priority processes will never have to wait for a processor core to be allocated. The key concept for CPU selection for this type of server is that the cores should be fast, and the sheer number of cores can be sacrificed to promote speed. As with all servers within the core zone, high-performance network cards should be used. Timestamping and kernel bypass functionality are key to optimizing network access. It may even be possible to get some of the functionality of the communications module to reside on the network cards. Network access speed will depend heavily on the requirements and the available budget. Remember that all of the interfaces in the core zone are likely to need to be tapped. Moving them to 100 gig Ethernet or faster means that all of the taps and all of the packet broker network will have to be able to handle these interface speeds. Ultimately, the limiting factor for the performance of the whole solution might be the cost of performant packet inspection engines. The lower priority interfaces, such as for the management zone, can definitely be kept at lower access speeds. While logging is important, it's a policy decision as to whether this should be a limiting factor for the exchange performance. It is much better to get the active matching engine to log tersely and to get a secondary server to perform the verbose or audit level logging. The alternative would be to get the active server to perform the verbose logging, which might impact its performance and ultimately its stability. Logs should be exported to a logging server in a timely manner, so that the log searches never have to happen on the active server. In some solutions, the function of the matching engine is supported by a cluster of 3 servers, and the responses to the market are made on the basis of a consensus decision. This solution architecture still supports such an installation, but requires 6 servers rather than 4. In the next video, we will cover the functions and performance tuning of the gateways. Thanks for watching. Please leave any questions in the comments and I will reply to them as soon as I can.